Hi, everyone. Welcome to the DStore AMA. We are here joined by DSA, Decentralized Storage Alliance, and the Supranational team. We're so excited to talk to you about this DSA Golden Gate release. And with that, we'll get started with Daniel.
Hi, everyone. Daniel here from Protocol Labs and lead of the DSA. Here to talk about the sealing releases and the DSA Golden Gate release. So first, just giving a quick overview, our aim here was to improve the P&L of storage provider businesses by reducing costs for one of the more expensive operations in the network. We ran a cost analysis a little over a year ago and just looked at all the different costs associated with being a storage provider and wanted to reduce the most expensive costs for the network as a whole. What Supranational has been able to do over the past year is pretty incredible. The impact that they're seeing right now is a 90% reduction in sealing server costs with greenfield optimizations that are tied to new hardware configurations. And then for PC2 and C2, these are brownfield optimizations that will be able to affect everyone's systems. We're seeing a 75 to 85% improvement and increased efficiency there as well. So just amazing improvements across the board, and all with the goal of reducing costs for the network. I'll cover here sealing objectives and the Golden Gate release, and then I'll hand it over to Kelly to do a little bit of a deep dive on the technical side, and then we'll move on to the AMA, where people can ask questions freely to either of us. Filecoin sealing is a computationally expensive operation, but a necessary one to secure the network and enable proof of ongoing storage. PC1, PC2, C1, C2, the whole process takes a number of hours and is a resource-intensive process for the network. Because of this, when we ran that cost analysis, we found that sealing CapEx can actually account for over 50% of total hardware CapEx, and that over $500 million worth of sealing hardware is locked in the network today. So this means that compute hardware is expensive, compute hardware can be difficult to access, and that translates to potential network bottlenecks. So we wanted to look at what those kind of effects on the network would be. And for new storage providers, there's a high barrier to entry to onboard to the network. For existing storage providers, it can be difficult to increase their sealing rate. And all of this is something that we wanted to address head on. So before we started working on the way to tackle this problem, we looked at what kind of objectives we wanted to set for the sealing software and that Supranational would be able to take on. The goals here were to increase storage provider profitability by reducing costs associated with sealing, by reducing the overall sealing server costs for the network. We wanted to reduce sealing CapEx with the new cost optimized sealing software and hardware configurations. We want to reduce sealing OpEx by actually reducing the number of sealing servers required to get a certain amount of sealing throughput, reducing overhead and equipment for sealing. We wanted to lower the barrier to entry for new storage providers with reduced requirements. And we wanted for existing storage providers to be able to accelerate onboarding data to the network by making it easier for them to increase their sealing rate. In summary, we wanted to reduce CapEx and OpEx for the entire network by optimizing Filecoin sealing through greenfield and brownfield software optimizations and hardware optimizations. Those were the goals. If we look at what the impact and the types of results that we're seeing from the software and new hardware, it's really amazing. So we'll dive into that, and then I'll pass it on to Kelly. This Golden Gate release is an initial early GA release. With the new cost-optimized sealing software, there will be additional releases that will make it easier for this software to access and for the optimizations to be realized by storage providers in the network. But we wanted to make it very easy for storage providers to access what is available today and open source software as it's being built, as it's being developed, as it's being released. And so we wanted SPs to start testing this new software, and we want storage providers to also start considering new hardware configurations that are associated with those greenfield optimizations. The new sealing software is really broken down into two different pieces. One are greenfield optimizations that are tied to new hardware configurations The other are brownfield optimizations that are going to be integrated directly into Lotus. For the greenfield optimizations, this is new PC1, new PC2, new C2 software that increases parallelization. So even though it might take a little bit longer to complete the process with the new greenfield optimizations, the increase in parallelization, the increase in the amount of sectors that you can do at once makes it so that the overall time to seal a sector goes down. The brownfield optimizations are ones that will be integrated directly into Lotus in Q3. So PC1, what used to be limited at 15 sectors in parallel, can now seal 128 sectors in parallel, which is just an incredible improvement across the board. Now takes around 5.5 hours. It used to take 4 hours, but again, because of the number of sectors that you can do in parallel, it's an incredible increase in efficiency for the PC1. For PC2 and C2, these are the optimizations that everyone's going to be able to realize across the board. PC2 that used to take 8 minutes now takes 2 minutes. C2 that used to take 16 minutes now takes 2.5 minutes. So really incredible performance optimizations here as well. And then if we dig in to some of the performance results and look at the specifics of PC1, PC2, and C2, this initial benchmarking is for CC sectors, but we expect to see similar results for non-CC sectors as well. Memory has been cut in half, with what used to be over a terabyte now is under 500 gigabytes. We talked about the sectors in parallel. That's an 8.5x higher throughput. For cores, there's an incredible amount of efficiency improvements here as well. With 4 cores per sector is what we used to see, and now we're seeing 4 sectors per core. For PC2 and C2, those improvements and time optimizations across the board will reduce CapEx by actually lowering the amount of GPUs. So storage providers will actually see freed up GPUs from these improvements, and it'll also reduce OpEx because they'll actually be able to reduce the number of sealing servers required for PC2 and C2, saving money on energy and hosting as well. If you look at those results and you translate those performance results to sealing cost optimizations, we're seeing sealing server costs reduced by up to 90%. And if you translate that and look at what it used to cost to purchase servers to seal 20 TIBs per day, the cost used to be over $200,000 to be able to do that. With this new cost optimized sealing software and hardware configurations, under $25,000 will actually be able to seal you 20 TIBs per day. A really big improvement across the board, cost saving across the board, making it easier to onboard to the network, making it easier to increase your sealing rate as well. So as mentioned, this is just the first of a number of releases. We want people to go out and start testing. We want people to think through new hardware configurations, but there will be other upcoming releases that will make this software a little bit more accessible. We're going to have orchestration software open sourced and released. We're going to have PC2 and C2 integrated directly into Lotus in Q3. We're going to be releasing DSA reference architectures that are hardware configurations tied to OEMs that will allow for storage providers to purchase hardware off the shelf that's compatible with the new cost optimized sealing software. We're going to be releasing DSA hardware upgrade instructions that will provide clear paths for storage providers to make use of their hardware today and optimize it for the new software that's released. And then sealing as a service will make the new cost optimized sealing software more accessible by being able to actually purchase sealed sectors from another storage provider that's running the software and hardware, or sealing as a service provider that's running this software and hardware as well. So that's an overview of why we worked on this, how we got there, what we're seeing as far as the results. I'll hand it over to Kelly now in Supranational to talk about some of the technical aspects that we're seeing from these releases. Let me see if I can just switch to share my screen. Kelly, you want to start with the logs?
Yeah, that sounds great. Thanks, Daniel.
Okay.
So while Daniel's pulling that up, as he mentioned, really the goal of this software was to improve the efficiency. And part of that was doing more sectors in parallel, overlapping compute, and for various sectors, the PC1 process, the PC2, and the C2 process. And then also to consolidate the hardware requirements into a single box to help lower the capital expenses and operating expenses as well. So what I'm going to walk through here, or I'll have Simon walk through briefly, is just a brief overview of the logs that are output when you run the demo application. And then once we just talk through briefly how to interpret the logs, we'll also show you a spreadsheet that we built that will visualize the results of the software on your system. So with that being said, I will pass it over to Simon to just talk through this briefly.
Sure. Daniel, do you want to scroll up to the top of that log file? And we can just walk through how to read this thing. So the first few lines here, you can see the first up through sector 128 there. It's showing you the topologies that it's going to use for the various number of sectors. So just to give you a little context, this run is from the Rust demo sealing run. It seals 128 32 gigabyte sectors per batch, and it does 3 batches in this run. So you can see the pipeline fully in effect here. And it runs them all in parallel, or it overlaps a number of the steps. And you'll be able to see that in this log. So the first part is just some overview of the configuration of the system. You can see then it says attaching to and several numbers there. Those are all the NVMe drives that it's attaching to use for the PC1 storage of the PC1 layers. And that's configurable in the config file. And then below that, there are a few parameters that show you the sector size, the node size, various things. Many of these won't change very much. It lists the offset and the slot size. That indicates how much storage is available on the drives, and how many slots you can store at a time for PC1. Mostly there just has to be enough capacity to store as many slots as you're going to use there. And in this case, it's 2. And then it gets into the actual work. So there are a number of lines that start with star, star, star. So 4 stars. And those are started in events for various steps. So the first one up there with the stars, let me see if I can find it, is for batch 0. It's locking slot 0. That means if you imagine these NVMEs, they have 2 slots for PC1. So this one is using slot 0, there's slot 0 and slot 1. And then it's starting PC1 in the next line. And those give you timestamps that you can see for these events, and you can then determine how long they take and whatnot. So then following that, it prints out several steps along the way for PC. These are for PC1. So you can see the individual layers getting processed. There are 11 layers for 32 gig sectors. And then when that finishes, it prints a little bit of information about the IOPS used and how long it took, 1437 seconds, which is about 4 hours. And then there's another set of stars that tells you that PC1 finished for batch 0. And then basically immediate after, it starts PC2 for batch 0. And at the same time, it locks the next slot, so slot 1, and it starts batch 1 for PC1. So now you have basically PC2 from batch 0 and PC1 from batch 1 operating at the same time. And so you'll see below that some log file comments or printouts interspersed for the 2 simultaneous things happening there. So you see partition layer 1, layer 2, and also partition 1, partition 2. The partition stuff is from PC2. And so PC2 for 32 gig sectors has 8 partitions. And if you go through the log, you'll see 0 through 7, partitions 0 through 7 happen there. And again, in the end, there's prints that PC2 finished, tells you how long it took, and you can see PC1 is still running. And then the next set of stars there is when PC1 finishes, it starts C1 for batch 0. And C1 will print, it does each of those 128 sequentially there. And if you scroll all the way through those C1s, eventually those finish there. And then it will start, I believe it's going to start PC2 for batch 1. And it'll proceed through PC2. And it's going to, in turn, at the same time, start the next PC1, reusing slot 0, reusing the storage from slot 0. So it's going to start another PC1. And then after that PC2 finishes, it'll start C2. So you can see all those events happening with some log files interspersed, and those will just keep repeating. This particular run does 3 batches. So in the end, if you work through the whole thing, you can see those 3 batches run and how they overlap. And that's basically what there is to the log file. And then Kelly can show you, we do have a way to visualize this a little bit better since there's a lot happening at once. and a number of these steps overlap, it can be a little bit difficult to follow. So we like to throw these in a Gantt chart, which makes it easier to see those steps and how they proceed. And I think it's probably a good time to look at that.
Yeah, that's great. Daniel, if you could share the Google Sheet. So as Simon mentioned, there are those events in the logs with the 4 stars. And what this Google Sheet does is it basically allows you to visualize your sealing pipeline. And the way that you do that is in each of those events with 4 stars, there's a Unix timestamp. And that can just be pasted into these yellow cells here in column D associated with the event that you see in the log. And so really all that you have to do to get this visualization and a summary of the performance on your system is to go through the log, depending on how many batches you run, and paste in these various Unix timestamps. What you'll see in column E is that the sheet will basically translate these Unix timestamps into a calendar or wall clock time. So this will give you a little bit more insight to decipher these Unix timestamps. And then if you scroll down a little bit further, Daniel, what this will also create is what's called a mermaid diagram. And this is basically code taken from the data entered above that can be input onto mermaid.live to create this Gantt chart that Simon mentioned. And so what you'll see over here on the right is the result of that diagramming software, where you can basically follow through batch 0, batch 1, and batch 2, and see when they're executing PC1, when they're executing PC2, what processes are overlapping. And really the key thing here is that in the steady state, when the software is run continuously, you are basically always more or less fully utilizing the GPU with the PC2 and C2 processes, which are the top 2 red bars here, while you're doing PC1. And so this overlapping of these various compute workloads really enables you to get high efficiency out of the system, ensure that the GPU is fully utilized, and that ultimately means that you can shrink down what used to be several boxes to do this number of sectors that may have been 6 or 7 different servers. You'll be able to shrink that down basically into a single server. And then if you just scroll up one more time in this, Daniel, what you'll also see is just some summary statistics for each batch, how long PC1, PC2, and C2 took. So as you'll notice, there's a little bit of variability in these, maybe around 10 or 15%, just related to exactly what's being overlapped and what's being performed there. But you get some nice summary statistics there where for these 128 sectors, you'll see something like 4.5 hours for the PC1 process. You'll see something around the 90 minutes to 100 minutes for the PC2 process for 128 sectors, which is about a minute per sector. And then for the C2 process, you'll see something in the order of about 140 to 160. So somewhere around about 2.5 hours, which is a little bit over 2 minutes per sector here. So we will share the spreadsheet for folks to use and copy into the DSA sealing Slack channel. So this will be available to folks. The demo application is on GitHub. And so folks will be able to run this on their own systems. They'll have instructions for how to run it in the README. And then ultimately we'll be able to visualize this through the spreadsheet and then the mermaid.live website. And with that, I think maybe we will go into the Q&A session. I'll pass it back to you, Daniel.
Awesome. Thanks, Kelly. Thanks, Simon. So I'm seeing a few questions here. Kelly, I will let you take these. You and your team take these. First one is from Nelson. Can we get a copy of the presentation? Absolutely. We'll send it out after the presentation is finished, and Kelly will share that doc. We'll also, in addition to having and posting documents and decks in the DSA sealing channel, we'll be putting up a DSA GitHub, which will allow for people that are testing it to put their hardware configurations and the performance that they're seeing in one place where everyone can see what kind of results they're getting. And hopefully we can open up some discussions around how to make certain adjustments and compare different systems and performance across the board. Kelly, I see the next question here from Bob. Is this release recommended for new storage provider setups, or should people wait until a later release?
Yeah, sure. So I'll take that. The software is able to be run today. The demo application is actually already set up to simply run several pipelines or varying sets of sectors. So, absolutely for new SPs, depending on exactly their needs, they may be able to just use the demo implementation or to make some modifications to that Rust file to suit their needs. So yes, it is able to be used today. As Daniel mentioned, though, there will be improvements coming around orchestration, integration into Lotus, et cetera. So I think it's certainly possible to use today, but it will only get easier in the future.
Next question here in the Q&A from Bob. With the shift from RAM to NVMe, what does this do to NVMe wear?
Yeah, that's a great question. So with the design of the software, we do the exact same amount of writes as the previous Lotus software. And so there is no change in the amount of NVMe writes, which are basically the limited resource in NVMe, as with the current software. So you'll see no additional degradation on the per sector basis with the new software than you would have seen with the existing software.
Next one here is from Sal. Will the C2 optimizations also apply for Snap-in?
Yeah, that's also a great question. I will maybe give my 2 cents and then let Sean jump in. The first thing I would say is that we have not tested the new C2 software for Snap-in. That said, as Daniel had mentioned earlier in the presentation, part of the new C2 software is new MSM and NT, which are the core GPU kernels that help us get some of the performance improvements. And certainly they can be applied. I also know that the C2 software was tried to be made as general purpose as possible so that it could work for a variety of snarks. But yeah, maybe Sean, I'll let you comment on the ability of the software to work with the Snap proofs.
Yeah, sure. We have not, as you said, tested it specifically with Snap-in. However, as you stated, it was generically improved. So the core functionality of the Groth 16 proofs was improved. It was tailored more towards C2. So there were things where we saw with window post where there wasn't much of a gain there. They were continuing to add features that will help support window post as well. And if we're looking at just those 2 proofs, then if we cover the characteristics of them, then it should naturally fall out that any proof that you use the library on will be accelerated, which includes winning post and then everything else.
Next question here is from Nelson Chen. Greenfield optimizations are standalone and have not been integrated into Lotus yet. So this ceiling optimization can only be applied to CC sectors for now and not verified deals. This is a question around,
Sure.
Yeah, you got it, Kelly.
Yeah, the greenfield optimizations so the greenfield optimizations in terms of PC1 are not integrated into Lotus. And to the best of my knowledge, there is not a plan to integrate those into Lotus at this point, or at least with a definitive timeline. Some of these greenfield optimizations, the software is the same for both greenfield and brownfield. One example of this is the C2 software. That is being integrated into Lotus. That will be there in Q3. Similarly with PC2, there was a separate software release that is going to be integrated into Lotus. So at this point, the one piece that is not planned to be integrated into Lotus is the new PC1 software. And at this point, I don't believe that there's a definitive timeline for if or when that will happen. As for the ceiling optimization, the question was, can it only be applied to CC sectors? And the answer is that it can be applied to both CC and deal sectors. And in fact, there's a variety of ways that we support deals that were previously never supported in the existing Lotus software. So we support sort of 2 modes of ceiling deal sectors. One mode is if you have the data right at the beginning on the ceiling rig, then you will be able to just directly go through the ceiling process, quite similar to how it has happened in the past with the Lotus software. There's also a new model where if perhaps the data is in a remote location and you don't want to transfer that to the ceiling rig, what we have the ability to do is split the process of sealing a verified deal into 2 halves. One where you can do some very small computations on the server where the data is at, and you can send over a little bit of that data to the ceiling service. It will proceed with generating the full replica, and then you can pass that replica back to where the data is, and it can be added together to get you your verified deal. And really what this means is that you now have half of the bandwidth requirements for moving data around. So the software does support verified deals today. And in fact, it supports it in 2 modes, one where you have the data co-located on the ceiling server and one where that data is remote.
Reba, is there anything you would want to add to ceiling non-CC? I know you've been involved in some of the conversations around what that deal flow might look like.
Yeah, good question. We are definitely looking into various piecing apart some of the code that lives in proofs so that Lotus can start using it in parts, which is effectively a requirement for being able to use both the Greenfield software and not only for CC sectors, because the difference effectively, the Greenfield software actually doesn't care because the Greenfield software only produces what we call sector keys. The trick is that in the case of CC, the sector key is your replica. So after the Greenfield software has done its job, there needs to be another step performed by effectively Lotus Miner or Boost, like it depends how we organize things. This also ties into a little bit into the Boost v2 2.1, so to speak, architecture. But yes, so long story short, the Greenfield software is already capable of doing that because it does the part that is data independent. And whatever we do after this step, whether it's going to be integrated into Lotus or we're going to figure out software for this is to be determined and is work in progress and research.
I do also see that we have a question from John in just the main chat. So maybe I'll take that one before going on with the Q&A channel. John had a question that says, to what do you attribute the 10 to 15% variability in process time? So I think I will pass that over to Simon to maybe just provide a little bit of color on where that variability comes from.
Sure. You mean, as Kelly said, there's a lot going on in the system between PC1, PC2, C1, C2, there's GPUs, NVMe, is quite a bit of memory. There's just a lot of activity on the system. So depending on, if you run any one thing, you don't see a lot of variability, but when you start running a number of these things overlapping, they do impact one another to some degree, naturally. And so depending on which steps you're overlapping and how they overlap, you will see some variations there. And I think that's primarily where it comes from.
Yeah, next one here. The biggest gain is on PC1 for the Greenfield optimizations. Is synthetic POREP the thing that's keeping it from integrating into Lotus?
Yeah, maybe I guess I'll comment on the first piece. There were significant improvements really across PC1, PC2, and C2. We saw anywhere from a 4 or 5x improvement in throughput to close to up to 16x in some cases. So I think that it's really shared across the variety of steps in the whole sealing pipeline. As for synthetic POREP, that is not the thing that's keeping it from integration into Lotus. The one thing that is unique about the new PC1 software is that it stores the data as it's going through these layers and building these layers on disk differently than the current Lotus software. And so Lotus doesn't currently, with the current PC2 and C2 software, know how to necessarily read that data off the disk because it's used to basically a different type of format. And so that's really one of the reasons, at least today, that Lotus doesn't support it, is that it's just the rest of the pipeline is not configured to read data off in this new format. And this new format is a way that we get some of these efficiencies. That said, I think there's also, at least to my understanding, and maybe Daniel and Reba can comment, I think in terms of integration into Lotus, so there's another piece of this is that I think that there's a little bit of a push to disaggregate many of the functions that are in Lotus today to be more standalone, to allow more modularity, to allow more reuse, to allow more easier optimization and upgrades. And so I think that is maybe also an element, is that with the new Sealing as a Service APIs, it's now actually possible for this software to be standalone that wasn't necessarily standalone before or didn't have that ability. And so I think that's also one of the sort of motivations, is that now we have the ability to take independent sealing software and have it natively integrate with Lotus out of the box. And so there's less of a need actually today to do that integration.
Next one here is a good one from Johan. Any plans on implementing unsealing of sectors with these new optimizations?
Yeah, that's also a great question. So I think the first thing that I'll say is that we haven't tried it and we don't currently have any plans. That said, and I'll lean on Reba here, my understanding is that the unsealing process is essentially the same as the sealing process. And if you have sealed data and you have the replica IDs associated with that data, you will be able to take that, put that into the sealing software, and then ultimately get out a last layer that can be subtracted out of the sealed data to get you to the sort of unsealed data. So I do believe that the software could likely be repurposed to do bulk unsealing. I haven't we haven't personally tried that, and it's not on our personal roadmap. But yeah, Reba, if you have any comments there, it'd be great to hear your take.
Yeah, everything you said, Kelly, is correct. I would only add that for somebody who would like to offer unsealing as a service, where basically the data is being retrieved in sealed form from a storage provider and passes through a third-party unsealing house, so to speak, that automatically creates all of these sector keys, regenerates them. For somebody like that, it would be very interesting to be able to configure the Greenfield software to not store the layers, to effectively be able to spit out the sector key without knowing that it will not have to do any 3C after that or anything like that. And by doing that, the hardware requirements for unsealing as a service farm will be the same memory and CPU wise, but they will be much smaller NVMe wise. So that's my only kind of like almost a feature request, because if you think about it on your end, it actually will be relatively small amount of changes. It will be just get in a mode where you not even don't save, but just start throwing away layers that you know you'll not touch anymore, kind of thing.
Next question here is from Stefan. You mentioned that sealing can be reduced to just one server. That's awesome. Yeah, it's amazing to see that this can be consolidated into just one box. I've been running PC1 and PC2 in separate machines. Are there any reasons to continue doing this using these optimizations?
Yeah, I think there are potentially pros and cons of both. One of the big advantages of consolidating these boxes into a single machine is that you have less and faster data movement. So if you're running PC1 and PC2 in separate machines, you have to basically send this data back and forth between these machines, and that can sometimes be a time-consuming operation. The other thing to think about is just from an operational capacity, this may mean that you have half as many racks that you're paying for energy, you're paying for hosting, you're paying for cooling. To the extent that you can consolidate this infrastructure, there may be some operational advantages. That being said, it's certainly possible to continue to run these in separate boxes. There shouldn't be an issue, but there may be some benefits to perhaps consolidating these into a single box.
Seeing another question here from Sal. With how the data is stored on disk, would it also be possible to unseal quickly a small part of a sector? For example, filled plus bot verifications.
It's a good question. I'm not super familiar with the fill plus bot verifications, but I don't think that there's necessarily anything inherent in how we store it on the disk that will necessarily make reading faster. We just make reads more efficient during the batch sealing process. So with the way that we store these various PC1 sectors on the disk, we're able to basically get 128x improvement in the reads. So it does help for the sealing process, but I don't think that it's going to necessarily help you unsealing any faster. The other piece is that once you finally store the entire sealed sector on the disk, it's actually in the exact same format as it is today. The only time when it's in a different format is when we're actually going through the PC1 process. So my guess is that there will be no change here because the sealed sectors are stored exactly the same as they are today. It's only in a little bit of a different format during the PC1 process.
Question here from Nelson. Do you have a reference architecture for a single box implementation? And maybe, Kelly, we can talk through what a single box implementation would look like from a high level hardware configuration aspect.
Sure. Yeah, there are a variety of configurations that you can do for a single box implementation. And as Daniel mentioned at the start of the call, the goal is to publish a variety of these configurations that can be purchased off the shelf or just built by sealing providers on the DSA website, and perhaps even on a DSA GitHub where we can have the community discuss what they're using, what they're buying, what sort of efficiency that they're sealing. But yes, we do have a reference architecture, and we're happy to share that, and it will be published on the DSA resources here in the future. At a high level, just to share, there's a few core components that are in the reference configuration. And I'll talk through those maybe briefly. So the first one that you need is if you want to seal up, if you want this single box configuration, meaning you want to seal up to 128 sectors at a time and be able to do PC2 and C2 in parallel, you need a 64 core system. The reference configuration we've been focusing on are AMD 64 core systems. These could be Threadripper Pros, these could be Epics. Generally, we are targeting Zen 3 and beyond, though we have had folks that have run the software on Zen 2, but the SHA performance for PC1 is very good and even better, not only on AMD systems, but on the Zen 3 architecture. So that's the first thing that you should look for in one of these boxes is a 64-core Zen 3 processor from AMD. The software, again, should work on, it can work on Zen 2, likely work on Intel, but if you want to get this optimal efficiency, that's the recommended hardware from a CPU perspective. The next most important piece is a sufficient number of NVMe to support both the IOPS requirement of PC1, but also to support however much data you need to store to be running multiple pipelines of the Sealing pipeline. So from an IOPS perspective, we generally see a need for around 8 to 9 million IOPS is the requirement there, which generally means you need about 8 or 9 NVMe drives to support the PC1 process. If you want to do this all in a single box, we also require a couple more NVMe drives for the PC2 process and also for just the host disk. So in general, what we're recommending for these single box architectures is that you have something on the order of about 14 NVMe drives. We recommend the PCIe V4 drives. So that's what you want to look like at from a storage perspective. So that's the second most important consideration. So we've got a 64-core processor, something like 12 to 15 NVMe drives. In terms of storage capacity, this really depends on how many of these pipelines you want to run in sequence. So we recommend either the 3.84, I think, or 7.68 terabyte drives in terms of the capacity of those drives, but this is up to you for how much you want to run. And then the very last component is just the GPU. The software is written for NVIDIA GPUs, so that is a requirement on the reference configuration. What you want to do is if you want to fit this on a single box, you need a relatively high-powered GPU. So on the consumer side, that's going to look something like a 3090 or a 4090, or maybe two 3080s or two 4080s. So that's what's required there. From a data center side, this could be something like the new L4s. I know folks have been testing. They've been testing the RTX 6000 ATA generation. And so really, you could just want to look for those data center side equivalents there for the NVIDIA GPUs. So it's also like A10s are applicable, but really just more of the higher end, last couple generation NVIDIA GPUs, all of those will work well.
Kelly, I just wanted to ask a follow-up question. I put it in the chat as well for everybody else. Have you guys had a chance to explore at all SHA-2 ARM chips?
We haven't explored SHA-2 ARM chips. That's maybe for it. So it's possible that those would have good SHA performance. I know that we have done some work with that in the past. When we focus on the reference configuration, what we wanted to look for is things that were highly available and also had sufficient PCIe lanes to support all of this NVMe that needs to be attached in this new type of configuration. So I know that there are some ARM server providers like Ampere and others, but we haven't tested those sort of ARM server-based systems.
And if the community wanted to take their hands at testing those, what would they need to do? Would this even compile on today or not really?
I'll maybe let Sean take that. I believe it would, and I believe that for SHA we used the. Oh yeah, go ahead, John.
Yeah, no, it's all written in assembly, so there's no chance it'll compile on anything other than very recent AMD and Intel processors. Yeah, I think another key point on it is ARM implementations of the SHA instruction can be really good. Believe it or not, even like your iPhone does SHA blazingly fast. However, what we're trying to accomplish is the parallelism. We're looking at this as if you want to save money, it's more of a throughput game. If you wanted to just seal a single sector, you don't need a lot of equipment, and you could probably do it slowly because you're probably not bound by time. So our key focus has been trying to use the machines that have a high amount of parallelism that we can get across, not just in the cores, but also across cores. And I'm not aware of what ARM-based processors exist that would support that.
But I guess if somebody wanted to try an ARM-based processor, they could rewrite the assembly code for the SHA instructions, and eventually that would be the main piece that has to be adapted to ARM.
Really great questions across the board. Any other questions before we close this out? I think we covered a lot. All right. That is the overview of this release. If you want to learn more, please go to the DSA website, check out the SuperSeal GitHub, go to the DSA Sealing Slack channel. We encourage everyone to start testing, start looking at this new software, start thinking through new hardware configurations, and we'd love to start conversations in that Slack channel across the board. Hope that was helpful. Thank you all for joining. We'll post resources in the chat and over Slack.